and we have two speakers, Dante and Fede. Let me do a quick introduction to them before I hand it over to them. Dante and Fede are both from Buenos Aires. Dante has been part of the data engineering team at Jampp for 2 years. But something interesting he mentioned, that he's also a circus performer. Oh, okay. I don't know if we get to see anything today, but it's good to know. Thank you for sharing that insight. And Fede is leading the DevOps and data infrastructure teams at Jampp. He's also from Buenos Aires. Spent more than 10 years in the IT industry on infrastructure, cloud, and data solutions. And I don't think he'll do any circus performance, but he is a hiking enthusiast. Seattle, where I am, also is a great place for hiking. So if and when this COVID thing gets over, if you come this way, we could go for a hike together. And there's a couple of these little mountains that people climb here, the Mount Si, which they use for prepping up for big mountain climbs as well. So hopefully, we can get to see you in person one of these days. But if not, we'll continue with the meetup in a virtual format. And I will stop sharing my screen and give you a chance to present your deck. Over to you then.
Thanks, Hamid. So I'll share. Yeah. So hi, I'm Dante, as Amit said, and I'm joined by Fede. And we'll be talking about using Presto in a context of high volumes of data within a business model that has naturally low profit margins. So optimizing for cost is crucial. So what do we do at Jampp? We basically conduct programmatic mobile marketing campaigns, and we have two campaign types: user acquisition to find more people to install and use an app, and app retargeting to re-engage existing users. So we do this through a real-time bidding system in which whenever an ad spot is available in a device, an ad exchange fires up an auction in which Jampp participates. This auction comes with some contextual data on the device, so we can use the data with our predicting algorithms to set a price for the bid and whether to bid or not. So when we decide all of this, we send the bid, and if we win, we can show an impression or an ad at the device. This model, all of this has to be done in 70 milliseconds or less. So there are actually millions of auctions running on at every given minute. So all of this leads to what we call the ad tech funnel. As we saw, the auction leads to a bid, which is an impression, and also then we have clicks and installs and events. As you might imagine, every step doesn't necessarily continue the funnel. So not every bid leads to an impression, and not every impression leads to a click, and so on. So actually, each step has an order of magnitude in decrease in volume. But also, the data criticality increases with each step. So installs and events are rare, but very important to keep all the messages and information. But auctions, for example, are very frequent, and we actually don't need to store all of them. So to optimize costs, we actually sample auctions, for example. We store about 25% of them, but we have to make sure that every click and every install and event is safe and kept. So given all of this, each table has different access patterns because of the volume and the nature of the data. So we need different partition schemes in each table. Going on to the data lineage and the table themselves, we have one of them per event type, but we also have many more event types. We have organic installs and events, which are those that occur naturally in the app. Whenever a user does something without an ad, that's an organic install or an event. And those are sent to us from the clients. We also have event types that are meant for tracking the performance of a campaign. And We also have a bunch of tables that are denormalized data from every other table. Joins and unions that further down the line will increase queries queries up of speed queries up. So our data infrastructure. We have 3 steps basically in data ingestion, data manipulation, and data querying. So for data ingestion, we have our pipeline unit, which it's basically a stream of data with an internal data source, which sends the message to Amazon Kinesis streams. And through Apache Flume, we store it in Amazon S3. I call this a unit because we have one per event type. We used to have them concentrated, many event types per Kinesis stream, for example. But we've been focusing on modularity and separation of concerns, which allows us to optimize for cost without fear of losing critical messages. So going back to bits and clicks, for example, we can optimize the bid pipeline to minimize costs at the cost of reliability, but the event and clicks pipeline is much more robust. So, and also something that I like to mention, in this pipeline, we saved a lot of cost by replacing AWS Lambda plus Firehose with Apache Flume. So I'd recommend to give it a try if you have something like this. So the next step is ETLs and data insertion. We do that with Spark and Hive, and we also orchestrate it with Airflow. Spark and Hive are very reliable for ETLs and insertion. Both run on top of Yarn, so they can live together on the same AWS EMR cluster. More on that later. And we use the Hive Meta Store as the main interface within engines, and also with Presto. So Spark, Hive, and Presto all interface through the Hive Meta Store. And also, I'd like to mention that Airflow is an amazing tool for scaling and orchestration. It's very flexible and robust, and we use it a lot. So I'd also recommend it, giving it a try. So we come to Presto. Presto is basically our main interface with the whole data warehouse. Internally, we use Spark and Hive to move data around and to perform insertions and everything else. But the querying of the data is basically almost exclusively done through Presto. Either our team or every other team in the company. And through the years, it actually became very important for us to maintain a reliable Presto, because there are lots of production-ready applications that are using it constantly. So we use it for ad-hoc queries through Apache Superset, or templated reports through a custom UI, feeding our machine learning algorithms, constructing the data sets, monitoring data quality with a custom tool, building automatic audience segments, and lots of more stuff. So basically, it's the only way the data comes or goes, it's queried from the data warehouse. And some numbers to exemplify all of this. We have lots of bid requests. We have sent 100,000 of them per second. Not all of them go through the full funnel, but many of them become bids, impressions, clicks, etc. So we have a lot of data moving around, and we sometimes we have over 1,000 queries per hour. Obviously, it goes ups and down depending on the data science teams and everything else. But we have to be able to perform plus 1,000 queries per hour. To do that, we have 3 Presto clusters: one for production applications, one for ad hoc queries, and another one for our machine learning experiments and data training, model training. And the interesting part of this is that we have that on a cluster running on spot instances with a custom autoscaling. So we oscillate between 30 and 100 worker instances. And Fede will talk more about this, which I think it's one of the most interesting things we've been doing to cut costs at Jampp. So I'll stop presenting and hand it to Fede.
Great, thank you, Dante. I will start presenting myself. So there we go. You should be, just a second, please. There we go. You should be seeing my slide. So as Dante said, I will talk about how we manage our Presto clusters and our concerns regarding cost efficiency of them. And on top of that, how we monitor and how we ensure that the service is available for the whole company. So if we start to talk about the cluster management, the central component of our setup relies on AWS Elastic MapReduce, or EMR for short. In case someone doesn't know it, EMR is the AWS service to help you provision and manage the big data clusters for a lot of mainstream applications used in the industry, like Hive and Spark, and of course, PrestoDB in this case. And I want to clarify the good and the bad, small highlights. The benefits are pretty clear. You can find them everywhere. You can provision a cluster with a couple of clicks. It's super simple to spin up new clusters. It has flexibility to tune the whole cluster and every application with a unified interface that makes the living much more easier for my DevOps part, my DevOps role. So it's a breeze. And like every AWS service, it has a great integration with the rest of the ecosystem. So you can natively integrate like with S3 drivers, with DynamoDB, with Glue, for example, for metadata and stuff like that. And from time to time, they add new applications to the catalog. So you surely will find that brand new application that is being used in the industry eventually will be added to EMR. So it's very good to be already integrated with EMR, and just on one click, you already have that new application, for example. So, but what about the part of the not so good part, that the things that we'll probably find on a production cluster on a Saturday at 3 a.m., right? The dark issues that nobody talk about. So the first of all, it's a bad idea to mix YARN-based applications with applications using their own scaler, like PrestoDB in this case. That's because each of them will assume that they have the control of the whole cluster, and nothing good could ever come from that. It's a very bad idea. Another thing, it's a missing feature particular that became important for us is the usage of autoscaling on instance fleets. I will talk about this in a little later, but you can set autoscaling, or you can use instance fleet, but not both. They are not compatible between each other, so there's an issue there. And regarding PrestoDB in particular, we found two issues. One is that the upgrade frequency is kind of slow. I mean, the Presto is moving pretty fast, and the official releases it's very quick. And EMR is kind of behind those releases. For example, in the last EMR version, in 5.3.0, you have PrestoDB 0.2.32, sorry, while the last PrestoDB version is 0.2.37. So if you are expecting that bug fix, that new feature that Presto just released, you may have to wait a couple of months or weeks at least until EMR release that on their version. And on the other hand, EMR lacks of support for PrestoDB integration with CloudWatch, the monitoring solution on AWS. So you have almost zero visibility of how Presto is running. I mean, how many queries is running, if the queries are taking too long, how much memory the cluster has occupied, and stuff like that. So you have to do it on our own. I will talk about this in a couple of slides. So regarding our EMR clusters in particular, this is how we design them and how we are running. On one side, we have a single ETL cluster with Spark, Hive, and Test. Like I said before, those applications are yarn-based, so we can live together and coexist in the same cluster. And as Dante said, we are using them for running our ETL workloads. And on the other side, depending on the workload, we have 2 or 3 Presto clusters to target different kind of queries, like ad hoc queries, like mentioned Dante, like the feeding the machine learning training and generation of models, and other production level or staging workloads. One important aspect in all this is that we store our data on S3. We have decoupled the storage layer from the computing, so we are not using HDFS like the standard maybe solution, and that allows us to easily scale the compute layer. I mean, it's just instances and compute power that you can easily scale on demand depending on your workload. And the storage, we are leveraging the practically infinite scalability of S3, right? To store as much data as we want. To give you an example about the numbers that Dante said before, we are storing like 600 terabytes of queryable data. So that's a lot, and that's a great use case for Presto. So like we said before, each cluster is autoscalable depending on how many queries or how many queries are running or pending, depending on the use case. I will talk about this later. And we also have 2 shared services between every cluster. Those are the metadata store where we store the table schemas and the partitioning information, the metadata information about those tables. We store them on a MySQL database running on RDS, and a DynamoDB table to handle the EMRFS consistency checks. I don't want to extend too much on this, but S3 is eventually consistent internally. So if you plan to do writes and immediate reads on the data, you could not find already there. So you have to manage an external key value to manage those consistency checks and implement a mechanism of retries if you don't find a file that you just write. And that's EMRFS. It's almost transparent. You don't have to do anything about that. So moving to how we tune and set up our EMR clusters, we have a great feature there called Bootstrap scripts that allow us to run bash scripts on each node when it's provisioned. We can control the execution order of those scripts, so you can ensure that, or it's more probably that your script will be executed just the same moment that the software or application is being provisioned. So probably when these bash scripts are executed, Presto is not even installed yet. So if you plan to, I don't know, modify a file, a configuration file, or write a file in a directory inside of Presto configuration, for example, those elements are not there yet. So we have to implement some mechanism. I will talk about this in a minute. And in our case, we use those Bootstrap scripts to handle some parameters that are not supported from EMR interface. For example, the JVM config file, and some OS level parameters. And we also use these scripts to install user-defined functions, like, for example, custom code that we developed. And we also, some of them are open source to improve the performance of some queries on some particular use case to better analyze information, more data. So, as I said before, we will be running the Bootstrap script before Presto is installed, so we can modify those files. The most useful case, you can see it in this slide, that we're modifying the jvm.config file to, for example, replace the garbage collector setting and anything related to that file. And the hack we have to do is what you're seeing at the first lines of the script. Is that in fact we are creating a background script using bash here documents, the here docs, and that script will be looping in background until Presto is starting while we're checking the PID file. Once the service is started, we do whatever task we need, and Presto finally we restart Presto to apply the changes. So moving to the cost-efficient part, Dante mentioned before that we have some cost restrictions due to low-margin industry. That challenge forces us to leverage design patterns to reduce infrastructure cost whenever it's possible. And if we're talking about reducing cost, nothing beats the usage of spot instances. For the ones who don't know them, the spot instances are similar to regular on-demand instances, but with the particularity that AWS could reclaim that instance in any time, killing it. In return, AWS sells these spot instances to a much lower and dynamic price based on a supply-demand balance. And when I say it, much lower, is like 80% lower, so it's a lot. The issue is that the spot instances are inherently unstable, so we have to define our solution with that in mind. One particular recommendation, also given by AWS, is to diversify our instance families because of scenarios of massive killing of instances are mostly scoped to one instance type in particular. So when you have multiple instances, you reduce that chance of killing your whole cluster.
Fede, we should be wrapping up shortly. Yeah.
Okay, I will speed up. Okay, I will passing moving to autoscaling. We found that our ad hoc clusters should be are defined by a usage pattern very focused on usage on office hours. So trying to reduce the size of those clusters will reduce up to or save up to 70% of our node hours per month. So autoscaling is a big feature. To sum up, everything we are facing here will allow us to reduce or compare what's spending on an on-demand cluster of a fixed site, let's say for example 100 nodes, versus an autoscaling cluster with spot instances. We can see here that we will be spending, or we're comparing a cluster of 52K per month versus just 9K per month. That's a lot of money, so it really does worth it. How we implement the autoscaler, I will pass very fast for this. We implement our custom solution for autoscaling based on a serverless mix of service and a central engine with Lambda to scale to take the decisions when to scale based on information from CloudWatch alarms and parameter and state storage on DynamoDB as key value. And the decision when Lambda decides that the cluster needs to be scaled up or down, it just modifies the instance fleet parameter on the cluster, changing the cluster size basically. I have to move along, but we monitor all of this with a solution with Prometheus, with two exporters, one low-level exporter on JMX and one high-level exporter using an HTTP scraper. The low level, as I said, use JMX to get the data, and the high level use the Presto HTTP endpoints, D1 cluster and D1 query to get what queries have been executed and get counters of what information, what our users are using on the cluster. Here are just examples of what we are querying. As I said, low and high level. I move along. And for closing our next steps, what we are planning to do, one is upgrade to EMR 6.0 that it comes with Apache, with Hadoop and Hive on Amazon Linux DOS. are not -2. Sorry about that. We plan to orchestrate our own Presto cluster using standalone EC2 instances, I mean, without EMR. We are planning to open source some components like the Autoscaler and the exporters I mentioned. And that's it, that are kind of minor. The last one is very important. We're planning to move Airflow to Docker on containers with Nomad and our Kubernetes orchestrator. That's it. Sorry for the last rush, but I think we have 2 minutes for Q&A. Sorry for
no worries. Thank you, Dante and Fede. What we can do is, while you look at some of the questions as they come in, we will have the Twitter team come and do their part as well, so that they get enough time, and we'll have time to answer questions together at the end, if that's okay. So if you can stop sharing, then I can share my screen and introduce our next speakers.
Second, please. I
no
just
worries.
lost my Zoom window.
Did you move into a full screen mode? I think you're still sharing, but sharing your desktop.
Yes, the button. Sorry. There you go.
Okay, thank you. I will start my screen share. And while people can ask their questions, we'll either try and answer them online or we'll use time in the end.